Welcome to the first episode of Trainee Pearls, a new initiative brought to you by the EBMT Trainee Committee. First of all, I will introduce myself. I'm Carmelo Gurnari. I'm an Italian hematologist, currently enrolled in a PhD program at the University of Rome Tor Vergata in Italy, and at the moment working at the Cleveland Clinic Foundation in the United States. During the pandemic, experiencing the consequences that impact on the health systems and hence inevitably on our education programs, we all realized that there is still much to do for the young hematology community. Indeed, we benefit from social media, which enabled us to unite beyond the borders of each other's countries, sharing opinions on possible improvements and educational initiatives. It is under this spirit that the EBMT Trainee Committee created Chimera, the first ever online and open access education e-course from trainees for trainees. Also, together with the chairs Claire Horgan and Nicole Gagelman and all our EBMT Trainee Committee members, we have devised another brand new initiative to deliver the most important messages, the pearls, of high-profile research works in hematology and bone marrow transplant to our fellow trainees all over the world. The topics will span from classical hematology to more focused bone marrow transplant research in order to give a broad overview and keep the knowledge of our young hematology community up to date. A unique aspect of our initiative is the way in which the selected research article will be discussed directly with young authors who have been involved with the published work, thereby creating an interactive chat peer-to-peer, from which we will try to grasp not only the medical messages, but also some tips on how to design and conduct high-profile research works. We all hope you will enjoy this new initiative and stay tuned for our upcoming Trainee Pearls. So welcome everybody. Today we have the pleasure to have with us Sushree Sahoo from the Department of Hematology of St. Jude Research Hospital in Memphis, United States, and the Department of Pediatrics and Adolescent Medicine, Division of Hematology and Oncology of the University of Freiburg in Germany, to discuss about the recent paper published in Nature Medicine entitled Clinical Evolution, Genetic Landscape and Trajectories of Clonal Hematopoiesis in SAMD9, SAMD9L syndrome. Did I say everything okay, Sushree? How are you today?
Everything perfect. That was really on point.
Thank you for accepting our invitation. Can I ask you, where are you physically right now, USA or Germany?
I'm in USA.
Perfect. So let's start our chat on your research work. Could you explain us why SAMD9, SAMD9L genes are important in hematology?
First of all, thanks, Carmelo. Thanks for this whole podcast interview, and thanks for having me here. So I will start. Your question is how SAMD9-9L is important in hematology. So it was not until probably 2010 that anybody knew about SAMD9-9L in the field of hematology. Before that, it was just two genes which are more involved in antiviral responses. Then in 2010, in JMML patients, a study came out where those genes are deleted almost in 25% of the JMML cases analyzed in that study. Then it was in 2016 that SAMD9-9L started to get associated with human syndromes. Those syndromes manifestations were very different. SAMD9L was more neurological, whereas SAMD9 was more gastrointestinal with enteropathy syndromes. But the common denominator there was those kids, they were developing myelodysplastic syndrome, and they were also developing loss of chromosome 7 that contained the mutant SAMD9 and 9L gene. That's how the importance of SAMD9-9L started in hematology. And this, sorry.
To clarify for our young fellows listening to us, this is obviously all germline carriers and pediatric patients, correct?
Yes, these all are germline carriers and pediatric patients. I guess until now, there was one study from our group in Hematologica where we published a 40-year-old male having a SAMD9L mutation, and he developed MDS at the age of 30 something.
Okay.
remember really well. Yeah.
So pretty young for an
Pretty
MDS,
young.
and probably a germline contamination of this little fraction of MDS arising very early. Okay, so I read that you first studied, as you were mentioning, the clinical, either hematological or extra hematological manifestation of germline SAMD9 and SAMD9L mutations. Could you tell us a little bit more about that?
Yeah, about the hematological point of view, these genes are growth inhibitory genes. So what we saw because of these mutations, which are extensively growth inhibitory, the marrow was completely empty. They are majorly hypercellular marrow with cytopenias. So a common MDS subtype in pediatric MDS that we say is refractory cytopenia of childhood. That's what we saw in the marrow of those children. In non-hematological phenotype, it is a little bit more diverse because there you will have a group of patients that does not have any non-hematological phenotype. Then there is a group of patients that have a spectrum of non-hematological phenotype. By spectrum, I mean some will have non-hematological phenotypes affecting, let's say, neurology or urogenital phenotypes or just skin or psychomotor development. And there will be some which is more in the severe end and they have almost everything. That multiple organ systems are affected, which includes the nervous system, your urogenital system, your enteropathy system, and also there are certain psychomotor development issues too. So one thing we came to know from this study is SAMD9-9L are two genes where the non-hematological phenotype also are very similar, and that's why we call it as one syndromic disease rather than two different entities. So yeah, that's more about it.
Okay, and from these analyses, can you tell us if is there any clinical red flag which should alert the attention of our fellow trainees to suspect if they have in front of them a patient who possibly may carry a germline SAMD9, SAMD9L mutation?
So yes, the good thing about this study where we had so many patients to analyze, we narrowed down certain features which can be considered as SAMD9-9L specific phenotypic features. So one feature is ataxia. So ataxia is a neurological phenotype that we have seen specifically in SAMD9L cases. We don't see in SAMD9 patients that much. Then you have this phenotype of transient mono 7. Those cases, sometimes they have monosomy 7 and they kind of resolve their monosomy 7 over the period of time, and their cytopenic counts are also improving and their blood count also improve. Then another thing is for SAMD9 patients, they present at a very early age if they have a very severe syndrome, and they have growth retardation phenotypes, and they have very severe urogenital phenotypes. That once you look at it, the syndrome is called mirage syndrome. So you will see that manifestation there. So these are very specific features that you will find. But more generalized feature is if you have a SAMD9-9L mutation and you have a patient also loss of chromosome 7, and by doing germline testing, you see a germline mutation instead of being 50% is actually decreased in frequency. That is a big red flag in hematological setting. That's when you start to follow these patients and make sure if the monosomy 7 is developing in the leukemia side, or the monosomy 7 is kind of stable and it's slowly resolving. So this is another hematological phenotype that one has to take care when they are dealing with a SAMD9-9L patient.
I see. And what about the immunological part?
Immunological part is very specific to patients with mirage, actually. So if you have a very severe syndromic feature, then you see the immunological phenotype. But if I talk in the context of pediatric MDS, we don't really see that much immunological manifestation in those patients.
I see. Thank you. Yeah. So is there any specific genotype, phenotype association aside of like more frequent features in the SAMD9 and more others in the SAMD9L?
There is only two features that we have seen for SAMD9L. It is more ataxia that you see only in those patients, as I said before. SAMD9, no. Then you have those specific genital phenotypes where you have developmental issues which are sexual organs. That is more specific to SAMD9, but not in SAMD9L.
I see. And I read also you had like a very nice also summarizing figure at the end of your paper regarding the clonal trajectories that this patient have. And this is very important also for us, for the clinical fellows, because we have to make clinical decision and to know, to be able to predict the clinical trajectories of this little patient is important as to our therapeutic management. Can you tell us something about that?
Clonal evolution is a very essential part of those syndromes. So you study adult hematopoiesis, right? Adult MDS. So you know how clonal hematopoiesis in there, and it is always associated with leukemia development. But in SAMD9L, clonal hematopoiesis can be two types. One can go to leukemia development, one can be just benign, and it can also help in revertant hematopoiesis, meaning the hematopoietic potential is actually reverted back and they have functional blood cells. So SAMD9L patients, we divided into two groups. One group where you don't have any clonal hematopoiesis, you just have the germline mutation. And those patients, they have a very chronic cytopenia. They don't show any kind of, how do I say, heterogeneous cellular population in their hematopoietic system. And they kind of show a very stable RCC kind of phenotype. Then in the second set of patients, we see clonal hematopoiesis where the mutation is lost as loss of chromosome 7. And this loss of chromosome 7 can either disappear or it can progress and acquire additional mutations, which results into the leukemic transformation. Then they can also have a second SAMD9L mutation as a somatic mutation that is occurring, but what we saw in our cases is in cis, like in the same allele as the germline. And those mutations, we call it as rescue clones because we saw they can rescue the pathogenic effect of the germline mutation. The third is the corrected clone that we call natural gene therapy, basically, where the chromosome 7q arm, the wild type arm, is duplicated and you have uniparental isodiazomy. And those patients, they have functional hematopoiesis. We have followed cases up to 20 years and the person is doing great and the hematopoiesis is completely reverted back. The interesting thing is a person can have all those clones at the same time.
Wow.
Yes, and how they are going to compete with each other, which is going to take over what, we need more cases to really understand that part of those diseases.
I see. So a question is also, you mentioned 20 years sometimes. So like, what is the timing of this clonal evolution? Can you tell us something more about this?
What we have seen is more early stage, like if the patient is diagnosed at a very early age between, I can't really demarcate the age time, but we have seen majority of those cases are as early as less than 5 years. We have seen they actually enter into this clonal evolution thing where they have different kind of clones that are competing with each other. And the cases which have no clonal evolution, they are more in the age spectrum where they're towards 10 to 13, 14 years, adolescence age period. So this clonal evolution, what we saw is more associated with at a very early age where the dynamics is happening.
I see. And when they do progress, do they have any particular somatic pattern of lesions that they acquire?
The somatic lesions are very different than adult if we compare in that direction. So usually the mutations that we saw was in genes like the KRAS and RAS genes. We see SETBP1, ASXL1 genes, PTPN11, CBL, ETV6. These are the genes that we saw. And what we noticed based on our single cell DNA sequencing analysis on few patients, that secondary somatic hit always occurs at the top of monosomy 7, that is loss of chromosome 7. We have not seen cases where it occurs as a separate, at least in single cell DNA sequencing. And we did only one patient that we did with CFU analysis. There we saw monosomy 7, then it progressed to acquire ZBP1, and then those monosomy 7 ZBP1 progressed to occur as ASXL1 mutation. So it is kind of a clonal progression. But at the same time, in the background of monosomy 7, we also saw PTPN11 and NRAS as separate clones. So you can have multiple mutations, but they all always occur at the background of monosomy 7.
So to summarize, there's basically a bone marrow failure signature in the clonal evolution of these patients, because these somatic hits are the same that, for example, we see in patients after aplastic anemia and PNH progress to myeloid neoplasia. There is like this chromosome 7 signature, if you allow me this.
Absolutely, you're right. Yeah.
Right? Yeah. This label regarding these ASXL1, RUNX1, ZBP1, these are frequent, and also RAS pathway mutation that you mentioned, KRAS and RAS, CBL, PTPN11. So this is very fascinating, and I was very impressed by, first of all, the number of patients you collected. That was so much of an effort, and the fact that these peculiar disease is an example of nature curing itself. In some cases, at least, because we've read, and you've just told us that patient can also have different trajectories. So can you tell us about if there's any predictor of the somatic rescue?
Not that we know of, but what we did see that while we were trying to see the co-occurrence of different events, even the somatic rescue occurs along with loss of chromosome 7. We saw, what our hypothesis is that in SAMD9-9L, you have different germline mutations, unlike other diseases where you can have 1 or 2 hits that you find in all the patients. In SAMD9-9L syndromes, the germline mutations are occurring throughout the gene. So you have the very different mutations, and there might be 1 patient per mutation or maximum 2 to 3 patients. It is not co-occurring. And those mutations have different pathogenic effect. So some are highly pathogenic, and they have a very strong clonal pressure on the hematopoietic system to lose that mutation. And those are the cases that go ahead and probably try to lose the mutation by UPD events, that is natural gene therapy, or by loss of chromosome 7 or somatic mutations. Then there are other set of cases where the mutation is not that pathogenic, and there is not that much of pressure to lose it. So they just exist in a chronic cytopenic condition. So I would say it is more like the pathogenic effect of this mutation, where you can see such clonal evolution. And whether it is a rescue event or it is a malignant event, that is probably completely random, that we, at least at this stage, we think it's completely random and you can't put a finger on it, what exactly is causing that.
Absolutely, I see. So what instead, like all these genetic insights that are drawn from your research, tell us about the role of the bone marrow transplant in these kids?
Our cohort was a very retrospective cohort. So all our kids were transplanted before. So we really can't, this study can't really comment that if we would have waited and watched some of those kids who have not progressed, how they would have, their disease would have developed. Probably they would have self-cured themselves, we don't know. Saying that, I can always say that if you have a SAMD9-9L mutation and you have a normal karyotype, you have not developed any kind of malignant karyotype, you can probably wait and watch how the patient is progressing. If the moment you catch a patient with -7 karyotype, like loss of chromosome 7, that is when you have to be vigilant about what you want to take the next step, because that -7 is very tricky. It can resolve, you can get a UPD clone, or it can just progress to the malignant transformation. So that's when you start looking at the patient and following up to see if you really need to do the stem cell transplantation or not. That is the key there.
I understand. Yes, of course. And do you have any insights regarding like the timing of a possible somatic rescue when they acquire the somatic deletion 7?
No, that we don't know what's the particular timing. So we really, that's something that we can't answer from this study at this point.
I see. Thank you. This is like absolutely fascinating. It's like a example of natural gene therapy, as you mentioned, and very nicely done. Can I also ask you about, so you in the paper, I read you compare this patient with another example of a pediatric bone marrow failure, which is the GATA2 mutated patients. Can you tell us something a little bit more about discrimination of this patient? What are the differences between GATA2 and SAMD9L syndromes?
So, of course, one difference is GATA2 is a GATA2 deficient syndrome, and SAMD9L is more like gain of function, at least at this stage that we are calling it. As a hematological phenotype, SAMD9 cases are more RCC, like cytopenic, refractory cytopenia phenotype, but they're the subgroup of MDS, which is we call MDS with excess blast, that has the real MDS phenotype that you see more in the GATA2 patients. SAMD9-9L patients have much younger in age in compared to the GATA2 cases. This is another difference that we saw. But if I have to comment on the occurrence of mono7, it is quite similar in both the genotypes. What we do know that in SAMD9-9L, it is non-random, meaning it's only the chromosome 7 that contains the mutant allele will get lost. In GATA2, we don't know if it is random, non-random, what is causing there. But if you talk about the somatic landscape, that is the oncogenic landscape, it is very similar between both the patient groups. It is more driven by the karyotype, that is the -7 karyotype, than the germline predisposition.
Yeah,
that's what we saw.
Yeah. Okay. So last question. Thank you so much. As now we learned, I think, a lot about SAMD9, SAMD9L syndromes, and our fellows can now have a more clear picture of your research. So, of course, last question, I would like to be more of a practical advice for our trainees who are eager to understand how work like yours can be designed, devised, organized, produced. Can we talk about like the evolution of your paper, how it was conceived, and who worked on that? How was your time split, USA, Germany? Can you tell us about the journey of writing such a beautiful paper?
Yeah, absolutely. This is a tough question, to be honest. So, as you already mentioned, one of the biggest strengths of this paper was the patient cohort. And the entire credit of this goes to the EVOGUE MDS consortium. They are the ones who actually collected patients for 20 years for us to have a cohort of such a huge cohort to work on. So that's incredible. All the clinicians, everyone who has contributed to this. This was actually 50% of the study. It was conceived probably 20 years ago that people have already thought something like this will happen. Then the rest 50% is about what we make out of that. So that's about how we designed this study. This study actually started just to look after the SAMD9-9L things were getting published. We wanted to see what kind of germline mutations we have in our cohort. It started with a simple exploratory kind of sequencing analysis to see the germline variants. As we go ahead and saw the prevalence of those mutations, it was fascinating, and it was really something startling to us that really 8% of the cases have those mutations. That's where the journey started. And then we had this cohort, we had the opportunity to really look into the genetics of this cohort, and the clinical phenotype was so well annotated that we can do those comparisons. And regarding about who worked and how it happened, it was a team of people who actually got involved, from the diagnostic team to the bioinformatics team, who all got involved to make this work happen. And as actually to speak about myself, I spent 4 years dedicated to this project. So I was working as a PhD when I started this project in University of Freiburg. And there I was traveling to US probably 3 times a year towards the end of my PhD. And then I kind of divided my work between both the continents. So where we are doing germline functional analysis, the single cell DNA sequencing was actually established and done in the US in the St. Jude Children's Hospital laboratory. So yeah, so it was like a complete 4-year dedication along with multiple people's input with a 20 years cohort that actually brought this paper. So it's a lifetime opportunity that I got, and I feel really blessed about it, to be honest, really. Yeah. This story was not very easy for us. When we started writing that paper, the struggle was to make it easier for people to understand, because we worked with it for so many years. We understand it, but to put it in a language, that was difficult for us. So yes, that writing part, it took us a while to really put it in a way that it can flow together. And your questions were exactly the same way that we thought about it. So that made it easy for me.
Perfect. I'm glad.
to really explain, because it was going in that direction, the way we actually put it in the manuscript. Yeah.
Thank you so much. And we are also thankful for your time and all your explanation that will be very useful for our listeners. So I want just to thank you, and this was an amazing chat, and thank you so much for accepting our invitation, and for all our trainees that are listening to us, stay with us for the next episode. Thank you so much.
Thank you for having me here, and it was a pleasure. Thank you very much.